How's it going, everybody? Welcome back to my channel. In this video, we will look into solving the problem of the order agnostic binary search, which essentially is a modified binary search. Let's understand the problem statement in more detail. Say we are given a sorted array 40, 10, 5, 2, and 1. Our goal is to find the target 10 in this particular array. And if we find target 10 there, then we return as index, that is 1, or else we return minus 1. Apart from that, we have given more additional information that the array can be sorted in either ascending or descending order, and there are no duplicates. Let's start off with the brute force solution first. One straightforward solution would be to loop through the array and try to find the target inside the array. And if we find the target, then we return its index, or else we return minus 1. What's the time complexity of this brute force solution? Since we are looping through the array, the time complexity is proportional to the length of the array. So in this situation, it is O of n, and the space complexity is O of 1 since we are not using any additional space. Because we know that the array is sorted, is there a way we can use binary search to reduce the time complexity of the search? Just like the regular binary search, let's consider two pointers, one at the start of the array and another one at the end of the array. And we compute the middle pointer using the formula, and in our situation the mid pointer is 0 plus 4 divided by 2, so it's at index 2. We are also given that the array can either be sorted in the ascending or descending order. So let's check which order this is sorted in. We can check if the array is sorted in the ascending or descending order by just comparing the start pointer and the end pointer. We can have a flag say ascending that checks the first element of the array and the last element of the array, and checks if the first element is smaller than the last element. If it is not, then we know that the array is sorted in the descending order. So in our situation, the array is sorted in the descending order. The next step is we compare the middle element, that is 5, with our target, and 5 is less than the target, and because our array is sorted in the descending order, so all the elements that are after 5 will also be smaller than the target. So this means we can straight away discard all the elements after and including mid. And we do this by moving the end pointer ahead of the mid pointer. Now the new end pointer points at index 1. We recompute the middle pointer using the same formula, and the mid pointer is 0 plus 1 divided by 2, and we take the floor, so that is 0. So the mid pointer and the start pointer overlap. We compare the element at the middle pointer with the target. In our situation 40 and 10, since 40 is greater than 10 and the array is sorted in the descending order, all the elements that would have appeared before the before 40 would also be greater than 10. So we discard this subset of the array and move the start pointer one element ahead of the middle pointer. That is, we move the start pointer at index 1, and we recompute the middle pointer using the same formula. 1 plus 1 divided by 2 is 1, so the mid pointer also points at 1. We compare the element of the middle pointer with the target, and in our case the element of the middle pointer is 10 and the target is also 10, so we have found our element and we straight away return mid, so that is 1. So this approach is very similar to the vanilla binary search, except the fact that since the array is sorted in the descending order, we just flip how we move the start and the end pointer. What is the time complexity of this algorithm? Since we are using binary search, we are dividing the array at every iteration into half. So the time complexity taken is proportional to the log of the length of the array, and the space complexity is O of 1 since we are not using any additional space. Let's write the code for this algorithm. I'll write the code in Python and provide the links to the code in JavaScript and Python as well. Even if you're not familiar with Python, I'd highly recommend sticking to the video because once you understand the basic structure, it'll be fairly easy to write in any other language. So let's get started. If you think this video has been helpful to you up until now, then I humbly request you to please like the video and subscribe to my channel for the YouTube algorithm, just so that other people can also benefit from this video. Thank you. Let's get started with the code. Here I've defined the basic skeleton with a few input examples. Some of them are ascendingly sorted and some of them are in the descending order. The first thing we will do is initialize two pointers, that is the start and the end. The start pointer is pointing at the zeroth index while the end pointer is pointing at the last index. And we also create a flag that shows if the array is sorted in the ascending order or the descending order. We can do this by, so if the element at the start of the array is smaller than the element at the end of the array, then this means the array is sorted in the ascending order. While loop will iteratively keep dividing the array until we either find the target element or the start pointer becomes greater than the end pointer, in which case the loop terminates. And in every iteration, we will compute the middle pointer. Binary search usually has three different cases. The first one being the middle element is equal to the target, in which case we return the mid because we found our search element. The other case is where the middle element is less than the target. So this is the array in the ascendingly sorted order, and 10 is our target element. 5 is the middle element, and in this situation, 5 is less than 10. This means our target has to be on the right hand side of the array if it is ascendingly sorted. So in this situation, so if ascending, if it's ascending, then we move the start pointer ahead of the mid pointer. So the start becomes mid plus 1. Else, if the array is sorted in the descending order, which is in this particular situation, say 5 is still the middle element and the target is 10. And since 5 is less than 10 and the array is sorted in the descending order, our target has to be on the left hand side of the array, which means that we have to bring the end pointer before the mid. So the new end becomes the new end is mid minus 1. Similarly, in the last situation, if the middle element is greater than the target, and if the array is sorted in the ascending order, then we move the end pointer ahead of the mid pointer. So the end becomes mid minus 1. If the array is sorted in the ascending order, then we move the end pointer before the mid pointer. So the end pointer becomes mid minus 1. And if the array is sorted in the descending order, then we move the start pointer ahead of the mid pointer. So the new start becomes mid plus 1. And say we keep iteratively dividing the array, and at one point where the start pointer becomes greater than the end pointer, we don't have any array to further divide anymore. So in those situations, we return minus 1. Let's run this code. In all our in all the three examples, our output is exactly the same as the expected output. Hopefully this video was helpful to you, and if it was, then I request you again to like the video and please subscribe to my channel. Thank you very much.